Okay, so the third type of intermolecular force is hydrogen bonding, and hydrogen bonding only occurs between molecules where you have a hydrogen bonded to either an oxygen, a nitrogen, or a fluorine. So within the molecule, the hydrogen needs to be bonded to either an oxygen, a nitrogen, or a fluorine if you are to have hydrogen bonds between the molecules. So this is easiest to look at an example. Okay, so I have drawn water. Okay, so I've got hydrogen bonded to an oxygen, and then the oxygen is obviously bonded to another hydrogen. So this is one water molecule. Okay, these bonds that I've drawn here are obviously covalent bonds between the atoms in the molecule, and you have got oxygen more electronegative than hydrogen, so I've assigned oxygen delta negative and hydrogen delta positive. Okay, I've also drawn the lone pairs on my oxygen atom. So this is one water molecule, and then underneath I've drawn another identical water molecule. Remember, hydrogen bonds are an intermolecular force, so they occur between two different molecules. So I have drawn a hydrogen bond between the hydrogen in one molecule and the lone pair on the oxygen in another molecule. So the hydrogen bond is occurring between two different molecules. It is not within a molecule. Okay, and hydrogen bond, okay, has to be between a delta positive hydrogen. So I've chosen this delta positive hydrogen on the first molecule, but I could have chosen any of these delta positive hydrogens. And then it's going to go to the lone pair on the oxygen in the other molecule. So I'm going from this hydrogen to this oxygen lone pair. I could have gone from this hydrogen to this oxygen lone pair, or from this hydrogen to this oxygen lone pair, or from this hydrogen to this oxygen lone pair, or this hydrogen up to this oxygen lone pair. Okay, it has to go between the two different molecules. Okay, pick a hydrogen with a delta positive charge in one molecule, and then pick the lone pair in the other molecule, and that is going to be your hydrogen bond. Okay, so this is an example of a molecule that you've got hydrogen bonded to oxygen. You can also have hydrogen bonds between molecules where hydrogen is bonded to nitrogen. So I've drawn ammonia. So I've drawn two ammonia molecules. In each case, nitrogen is more electronegative than hydrogen, so it has a delta negative charge, which puts a delta positive charge on each of the hydrogens. You've also got a lone pair on your nitrogen. When I'm drawing my hydrogen bond, I've drawn it between the lone pair on this nitrogen and a delta positive hydrogen on the next molecule. I equally could have drawn it between this lone pair on this nitrogen and any of these three hydrogens on the next molecule. So it doesn't matter which hydrogen you're picking, it doesn't matter which lone pair you're picking, it just has to be from a hydrogen on one molecule to a lone pair on another molecule. Remember, these are intermolecular forces, they are between two different molecules. A third example, okay, so that's an example of hydrogen bonded to nitrogen. Now we need to look at hydrogen bonded to fluorine. Okay, so I've just got hydrogen bonded to fluorine. Again, fluorine's more electronegative. It has a delta negative charge. Hydrogen is delta positive. And I can draw a hydrogen bond between the lone pair on one of my fluorines and the delta positive hydrogen on the next molecule. Or I could have picked one of these. It doesn't matter which one. I could have picked any of these fluorine lone pairs and drawn a hydrogen bond between this lone pair and the delta positive hydrogen in the next molecule. Okay, so you will see what these molecules have in common, okay, is yes, they've all contain hydrogen, but they've all got hydrogen bonded to a very electronegative atom. Okay, so oxygen, nitrogen, and fluorine are all very electronegative. That puts a strong partial positive charge on the hydrogen. Okay, and that's important. You need to have a strong delta positive charge on the hydrogen. You only get that if it's bonded to a very electronegative atom, such as oxygen, nitrogen, or fluorine. Okay, the other criteria that's important is that this electronegative atom must have at least one lone pair. So you'll see fluorine has 3, oxygen is 2, nitrogen is 1, so they've all got at least one lone pair. Okay, and also that lone pair must be confined to quite a small orbital. So oxygen, nitrogen, and fluorine are all in period 2. Okay, they've all got their lone pairs in a 2p orbital, and 2p orbitals are quite small, which means the electrons in each of those lone pairs are forced quite close together because they don't have much space to move far apart. That means you've got quite a high density of negative charge in each of these atoms' lone pairs. Okay, so one criteria, you must have hydrogen bonded to an electronegative atom. The second criteria, that electronegative atom must have a lone pair, and that lone pair must be confined to a small orbital so that the negative charge becomes concentrated. You've got a high density of a negative charge. So for example, hydrogen chloride, okay, chlorine is a very electronegative atom, okay, that does put a strong delta positive charge on the hydrogen, okay, so it fulfills the first criteria. If we look at the second criteria, yes, chlorine has lone pairs, but because it's in period 3, each lone pair on chlorine is in a larger orbital. Those negative electrons within the lone pair can spread themselves out more, and you don't get that same concentration of negative charge. So with hydrogen chloride, although it contains a hydrogen bonded to an electronegative atom, okay, the lone pairs in chlorines are not, they're too spread out. You don't get that high concentration of negative charge, and so you do not get any hydrogen bonding between different hydrogen chloride molecules, okay? You only get it with molecules that have hydrogen bonding to oxygen, nitrogen, or fluorine. So if we just take a look at a few more examples of this. So I've just used simple examples. I've used water, ammonium, and hydrogen fluoride. So let's look over here at another example. In this case, I have drawn methanol. So I've got a CH3 bonded to an OH. So I've got oxygen directly bonded to hydrogen within the molecule. That means I can have hydrogen bonding, okay? So this oxygen will be delta negative, the hydrogen will be delta positive, and I can have hydrogen bonding between this delta positive hydrogen on one molecule and between the oxygen lone pair on another molecule. So I've just drawn two identical molecules and I have a hydrogen bond between them. I equally could have drawn this hydrogen bond between this delta positive hydrogen and this lone pair on this oxygen, okay? As long as you've got an oxygen bonded to an oxygen bonded to a hydrogen within the molecule, then you can have hydrogen bonds between the molecules. If I look at another example, okay, this molecule is called propanone. I've got hydrogens in this molecule and I've got an oxygen in this molecule, but the hydrogen is not bonded to the oxygen. If the hydrogen is not bonded to the oxygen, then you do not have your delta positive hydrogens, okay? Here I've got hydrogen bonded to carbon. It's not delta positive. Carbon is not significantly more electronegative than hydrogen, so you don't get that delta positive hydrogen, okay? Because you don't have that delta positive hydrogen, you're not going to have hydrogen bonds form between these two molecules. The hydrogen has to actually be bonded to the oxygen. Just having oxygen and hydrogen within the same molecule is not enough, okay? So you will have no hydrogen bonds between these two molecules. If we look at another example with nitrogen, okay, so I've got nitrogen here bonded to two CH3 groups and also bonded to a hydrogen. Because nitrogen is directly bonded to hydrogen, I get a delta positive hydrogen and I've got my delta negative nitrogen with my lone pair. I've drawn an identical molecule underneath and I've drawn a hydrogen bond forming between the lone pair of the nitrogen and the delta positive hydrogen on the nitrogen in the other molecule, okay? Similarly, I could have drawn a hydrogen bond between this lone pair and this hydrogen, okay? But if I look at another similar example, okay, I've drawn a similar molecule underneath, but I've replaced the hydrogen on the nitrogen with another CH3 group, okay? So I've got a molecule here that has nitrogen, it's got lots of hydrogens, but the hydrogen is not directly bonded to the nitrogen. Therefore, the hydrogen doesn't have the necessary delta positive charge. Therefore, you are not going to form hydrogen bonds between these two molecules, okay? It's really important that the hydrogen is directly bonded to either the oxygen, the nitrogen, or the fluorine if you are to have hydrogen bonds form between the molecules. It's worth noting that hydrogen bonds are the strongest of the intermolecular forces, okay? So when you have hydrogen bonds present between molecules, because they're stronger than the other intermolecular forces, those molecules are going to have higher melting points and higher boiling points because it's going to take more energy to overcome these hydrogen bonds than any of the other molecules. And indeed, where this is most notably seen is within water. So water has a relatively high melting and boiling point compared to other molecules that are a similar size to water. And the reason that water's melting and boiling point are higher, okay, is because of the presence of hydrogen bonds. Okay, you've got hydrogen bonds between all of those water molecules. They require more energy to break than your induced dipole and permanent dipole. Therefore, water has a higher boiling and melting point than other molecules of a similar size. Okay, so it's really important when you're talking about water that you don't say that water has a high melting and boiling point. Okay, it doesn't. It has a relatively high melting and boiling point. That word relatively there is important because it means compared to other molecules of a similar size. Water also has another unusual property, and that property is solid ice is less dense than liquid water. So you're hopefully aware that ice floats in water. The fact that ice floats in water tells you that the particles in solid ice are less tightly packed than the water molecules in liquid water. Now, this is not normally what we see, okay? We know from looking at particle diagrams that in a solid, the particles are tightly packed, and in a liquid, they're further apart. But in water, the opposite is true. In water, the molecules are further apart in ice than they are in liquid. I've got a diagram down here to show you that. So this represents water molecules in ice, and as you can see in ice that those water molecules are much further apart than what those water molecules are in liquid. In fact, in ice, you've got this open lattice structure with a lot of holes between all of these molecules. In liquid, those water molecules are much closer together than what they are in solid ice. Okay, so this is unusual. This is not what we're used to seeing. We're used to seeing in a solid, particles tightly packed. In a liquid, the particles slightly further apart. That's not the case in water. And because that's not the case in water, because you've got this open lattice structure in ice, ice is less dense than water, and ice can float on water. Now, the reason that water molecules take on this structure as a solid is because they are trying to form as many hydrogen bonds as possible. Okay, they want to form as many hydrogen bonds as possible, and so they orientate themselves in such a way that they can form as many hydrogen bonds as possible. And this causes them to take on this open lattice structure. So they do this so that they can form as many hydrogen bonds as possible, because energetically that is favorable. But in doing so, you end up with this open lattice structure. The water molecules are further apart in ice than in liquid, making solid ice less dense than liquid water, meaning ice will float on water. Okay, so this is an unusual property, and it's all to do with hydrogen bonds. In the next video, I'm going to go through the answers to the exam questions, which start on page 32. So have a go of them by yourself first, and then I'm going to go through the answers in the next video.